We have an example problem here. A 28 centimeter radius ball is uniformly charged with 72 nanocoulombs throughout its volume. Two parts. A, what is the electric field strength at R equals 12 centimeters inside the sphere? B, what is the electric field strength at R equals 35 centimeters, which is outside the sphere? Okay, so we have a sphere, a ball. I'm going to use capital R to represent the 28 centimeters. So this is the actual ball that is charged uniformly throughout its volume with a total charge of 72 nanocoulombs. Okay. So there's charge everywhere inside. This is some sort of insulator that has been charged. The easiest way to go about this is to use Gauss's law. If we think about the electric field, because of this symmetry of a beautiful sphere, electric field should be pointing outwards. There will be an electric field inside as well as continuing outside. The reason it has both inside and outside is because of the charge being spread throughout the volume. So in terms of choosing our closed surface, which we call our Gaussian surface, because we're going to use Gauss's law to talk about the flux through this surface. The purpose of this is to choose a surface that has symmetry to what this electric field looks like. And that symmetry is always directly related to the symmetry of the charged object. So let's talk about inside the sphere first. Inside this sphere. What I'm doing is I'm going to draw another sphere that's representing my closed surface or Gaussian surface. To have this symmetry, the sphere I'm drawing needs to have the same center as the actual charged sphere. So I'm drawing another little sphere in here. They share the same center. So this new one, this blue one, is my Gaussian surface. My imaginary surface that we're going to talk about the flux through. So we're talking about the flux through this new little sphere that I've drawn. This new sphere that I've drawn is not an actual object. It is not charged. It's just a closed surface to talk about flux. Now with symmetry, recall that the integral through the closed surface, if we've got the symmetry right, we should be able to say that this flux is simply E times A, meaning the strength of the electric field times the surface area that the electric field lines are passing through. So the conditions we had to meet is, one, that E is uniform, meaning it has the same value as it passes through the surface area. By centering my Gaussian surface, my little new blue sphere, by making that the same center, each side of this Gaussian surface, r, so lowercase r is the radius of my Gaussian surface. Oops, S. Because I drew this new Gaussian surface having the same center as the actual charged sphere, it is true that the electric field will have the same value as it passes through the surface of this new little sphere I drew. It is also true that the electric field vectors are parallel to the area vectors at any given point. These electric field vectors are pointing radially outwards, and my new little sphere, its area vectors are also pointing outwards. Area vectors are always normal to the surface, meaning perpendicular to the surface. And so we are meeting this condition that the electric field is parallel to the area, meaning the area vectors for the surface area is passing through. We know also, though, Gauss's law tells us that the electric flux can be calculated by knowing how much charge is within that surface divided by our constant epsilon naught. This is the relationship we're going to use to solve for the electric field. Okay, so back to the left, we're inside. We're going to say the electric field passing through this closed surface times the surface area of this same closed surface is equal to the charge within it divided by our constant epsilon naught. We're trying to find the electric field. The field lines, the electric field is passing through all sides of this little sphere I've drawn. So I want the surface area of the Gaussian surface itself. This new tiny little surface I've drawn that represents a point inside the actual charged sphere. Excuse me, so lowercase r is the radius of the Gaussian surface, which essentially for part A is 12 centimeters. We draw our Gaussian surface such that the electric field is passing at a point we're trying to find the value of the field at. So since this problem, part A, is asking us to find the electric field at that point, then we're going to say R for our Gaussian surface is 12 centimeters. I'm not going to put the value in until the end. All right, charge within. There is not 72 nanocoulombs within this new little sphere I've drawn. There is not 72 nanocoulombs within this Gaussian surface. That 72 nanocoulombs is spread throughout the entire 28 centimeters of the ball. Okay. To find the charge within that small surface, we do that using charge densities. Okay. Since this is specifically telling us that the charge is spread throughout the volume, we want to talk about volumetric charge density, rho. Okay, I'm going to write this on the bottom here. So charge density, rho, would be the total amount of charge divided by the total volume the charge is spread throughout. That's totally true. But it is also represented by the charge inside our small sphere, divided by the volume that our small sphere is covering. So there's two ways we can go about this. We know the total charge that's given to us in this particular problem. That's this 72 nanocoulombs. The total volume of the sphere would be 4/3 pi r cubed, where that radius is specifically the 28 centimeters of the ball that is charged. We could, if we want, actually calculate this value and then move forward, or we can leave this in terms of a ratio and equate it to Qn. One's not necessarily any better than the other, so that's really a matter of opinion. I'll go ahead and just equate the ratios for now. So I'm putting Qn is what I'm essentially looking for, because that's what I need to put in my Gauss's law equation. So I'm dividing by Vn, meaning the volume within my Gaussian surface, my closed surface I chose to draw, which is another sphere. It just has a different radius. It has that radius of 12 centimeters. So I'm using capital R to represent the radius of the actual charged sphere, and lowercase r to represent the radius of my Gaussian surface, my closed surface. If I leave this in terms of these ratios, I can go ahead and cancel out the 4/3 pi. If I solve for Qn, that's going to bring r cubed up to the top, and capital R cubed will still be in the denominator. This is what I will put, so coming back to Gauss's law, this is what I will put in for Qn. This represents how much charge is within this closed surface. So this approach, we're always talking about a closed surface, which was that smaller sphere that I drew. Okay, in this now, coming back to the left side, it turns out I can cancel the r squared with two of them on the right. If I solve for E, I get QR over 4 pi epsilon naught r cubed. Capital Q represents the total charge, so the 72 nanocoulombs. Lowercase r represents the radius of the Gaussian surface, which it represents whatever point inside the sphere that I want to find the electric field. 1 over 4 pi epsilon naught is the 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. So rather than write out the 4 pi epsilon naught in the denominator, I'm going to go ahead and just use my K. Capital R is specifically the radius of the overall charged sphere. So the 28 centimeters, which of course I want in meters. So let me go ahead and calculate this. So plugging these all in, I am getting 3538 and point stuff. But revisiting the problem, we're given 28, 72, 12. So we only have 2 sig figs. So we do need to round this. So 3,500 newtons per coulomb, or 3.5 kilonewtons per coulomb, or 10 to the 3. Either way, but we do want to consider significant figures. Okay, so this equation that we've come up with, where we had q lowercase r over capital R cubed, this equation is valid as long as lowercase r means where we find the field, where we're calculating the electric field at. Capital R means the radius of the charged sphere. This equation is valid only inside the sphere, and that's because of how we set everything up, how we accounted, for how much charge was located within that closed surface. It's totally possible, if we go back, I mentioned before, you can totally solve for rho, because we know the total charge and that total radius. So you could calculate that value and say Qn was rho times Vn. It's the same setup, just calculating in a different order, and plug this portion in for Qn over here. The equation would look a little bit different because we would be writing it in terms of rho as opposed to Q, but the approach would be the same. We're just calculating an intermediate step is all. We're going to find also that this equation will work at the surface. Now, you're not going to see that quite yet, but we will see that as we solve for part B. Okay, so this is just part A. We're calculating the flux through a closed surface that we have chosen, this Gaussian surface, but we have to be careful about the surface we're choosing because we need this symmetry to simplify the integral down to be just E times A. But again, spheres, this works nicely. We just draw another sphere. That's the closed surface we choose. And we talk about flux through that closed surface. So part B, we're asked to find the electric field at a distance of 35 centimeters. So a point outside of this charged sphere. So in my drawing, I'm still going to use a lowercase r to represent where I'm finding the electric field. This is going to represent the 35 centimeters, where it is that I want to calculate this electric field. What I want to do, again, is to choose another surface. I can't use that little blue one I drew because it does not encompass a point out here. I'm trying to find out how strong the electric field is out here. So I need to draw another surface. It needs to be another sphere centered on this original sphere, the charged object, the charged ball. So this is just a new Gaussian surface. So GS for Gaussian surface. It is a surface that has charge inside it. We're going to find the flux through this surface. Okay. Now I'm going to be doing a little bit of scrolling up and down. I apologize for that, but we need a little more room. So outside, our Gaussian surface is another sphere with a radius lowercase r, which we're going to set this up symbolically. But what we mean by this r in terms of answering the question is 35 centimeters, where we're trying to find the field. And this 35 centimeters is from the center of the actual charged object, is where we are measuring that from. Okay, by drawing another sphere centered on the actual charged ball, that is a sphere, we are again meeting these criteria where E is uniform, E is parallel to A, which means the flux through this Gaussian surface can be written both as E times A, so the strength of the electric field as it passes through this surface area of the sphere that has a radius of 35 centimeters. The flux can also be written as Q within the sphere inside over epsilon naught. So E is what we're looking for. We want to know the strength of this electric field as it passes through the surface. A is the surface area of the Gaussian surface, the sphere I drew that has a radius of 35 centimeters. So our next step is to figure out how much charge. So scrolling back so we can see the picture, if my computer screen will let me. We need to know how much charge is physically located within this sphere that has a radius of 35 centimeters. Well, the entire charged ball is in here. All 72 nanocoulombs will be within this new Gaussian surface. So for this new surface, I can say Qn is simply Q. All of it's in there. Okay. So coming back down, sorry, I'm sure it's a bit annoying to watch this scrolling. Q represents all 72 nanocoulombs of charge that the original charged ball, the actual ball that was charged up, the total charge it had. When I solve for E, bring this down, R squared, you will see also in the test notes that outside of a sphere, the electric field is 1 over 4 pi epsilon naught, which is the K. Q represents the total charge on this sphere, and then R represents the distance from the center. This is valid as long as lowercase r. Lowercase r represents the distance from the center of the charged sphere to where, well, to the point where you're finding the electric field. So this equation is valid for r is greater than or equal to capital R, meaning the radius of the actual charged sphere. Now notice I put it's greater than or and equal to, Scrolling this just a bit, this equation up here on the top right was what we came up with for inside the sphere. This is the equation for outside the sphere. Notice on the surface where lowercase r, where we're trying to find the value, is equal to the radius of the charged object, the top equation, the inside equation, Q, we plug in capital R for lowercase r, it's capital R cubed in the numerator, this becomes the same as if we plugged in to the outside equation, capital R for lowercase r. We get the same answer. These equations both give us the same answer for the electric field on the surface. We call this a boundary condition. Okay. So one of the biggest things is remembering we have to choose our own closed surface to talk about the flux through. And we need to make sure we choose that surface so that we can simplify the integral portion to be simply E times A. And then Q portion is generally determined by how the charge is distributed. So some sort of charge density.